I'll start recording. So this is a talk about teddy bears. Hello everyone. I'm Tesla. This is a talk in the Idris Developers Meeting, and the title is called Teddy Bear because yesterday I asked about what kind of topics are welcomed in IDM, and a moderator told me that people may want to hear about Rust or Haskell or Agda, but probably not teddy bears. So I just changed the title to teddy bears. Um, and here are some meta information about this talk. Now I'll be talking about Aya. Aya is a programming language with first-class types, just like Idris, so I guess the topic is relevant. And why talk about Aya in Idris Developers Meeting? Because Edwin Brady talked about Idris in Agda Implementers Meeting, so I guess that's fine. And there are some acknowledgements which I'm not gonna read them. And the prerequisites of this talk would be basic dependent type theory, and you should understand equation reasoning in dependent type theory, and you should have the idea what is definitional equalities or computational rules or reduction rules or whatever. Just the concept is important. And it may help if you know some cubical type theory, but only the QTT's extension type will help. And also maybe it will help if you know the type theory of the errand language, which if you don't know, it doesn't matter. I will introduce that to you. So let's look at some Aya code. Here's the natural number definition in Aya, which looks pretty much Haskellish, right? It's not very like Idris or Agda. It's like Haskell, and it's very obvious. I'm not gonna go into the details. The open keyword. So basically, a data introduces a module. You have to use qualified names to access the fields, the constructors of the module. If you put open behind data, it will bring the constructors to the outer scope. And here's some longer example where you have binary operators and automatic generalizations. So the binary operators are like you put an infix keyword before the definition's name, and you can put bind tighter after the name. So so cons will be parsed as an infix operator. You can see below. There's cons in the patterns, which is infix, and you can write bind tighter to tell the compiler that when you see a cons b equals c, a cons b is a whole, and you put that at the left hand side of the equals sign. And I believe this is a better way to use to do binary operator parsing. It's much better than using an integer or like something else. So here's a summary. We have Haskellish data type syntax, and data types are also modules, and we have infix operators. The precedents are specified by a partial ordering instead of an integer like in Haskell, or a float point number like in Agda, or a complex number like in Idris. We also have Lean and Agda style defined generalizations instead of Idris style. So look at here. We have a type called A. It's capitalized. It doesn't matter if you capitalize or lowercase it. As long as you define it, you say that A is a generalized variable of type, then it will add the A colon type behind the telescope of this function. And so if there are more complicated types, you can also specify them in this way. And Idris automatically infer the type of these generalized variables, but Idris only do so for lowercase types. It depends on people's opinion to see which one is a better design. And there are some advanced topics in case you are an expert in type theory. We have automatic and cumulative universe polymorphism. It's buggy, but it's only the solver is buggy, I believe, and the system is like in Lean or Aaron, but slightly different. We have a special syntax for specifying it explicitly, so it's kind of fine. We have some facilities for you when something doesn't work, and we're looking for help for someone to help us on this. Also, we have automatic inference of type checking order, which is also kind of buggy right now. But we can already do a lot of things. We can write a lot of mutually recursive definitions. So by having that, we have no need for special syntax like forward declarations, like in Agda, to do induction recursion or induction induction. So these two parts are for experts, and we have some obvious shell cases for beginners. And but what about GADTs? Because we have Haskell-ish data type syntax, we don't have the obvious way to do GADTs. So we have followed a paper in Tidy workshop called the simpler encoding of index types. We add a pattern matching in before the constructors to describe like when do these constructors available during the pattern matching. And this is not a actual pattern matching, it's just a way to specify when the constructors are available. So these pattern matching do not be covering, and they can overlap, and so this is kind of pseudo. So look at this fin type. If you put 0 here, both constructors don't match, so it's an empty type. If you put a blocking variable here, then we don't know which constructor is available, so the pattern matching is not allowed. If it's in Agda, it will say like, I'm not sure if there should be a case for F0 because I get stuck for the unification problem, something, and that's the same case. If you put successor of something here, then 2 of these constructors become available. And here's a function definition, which you can see we have forced patterns or inaccessible patterns, whatever you say. This is something interesting. I believe you're familiar with this in Idris, right? I think people work with fin type every day in Idris. There's one more complicated example, a slightly more complicated example. It's sized vectors. We also have the binary operator syntax here. We also have the pattern matching in constructors. And then we have a map function, which is guaranteed to preserve the size of the vector. I believe all of these are obvious enough to read. It's very familiar syntax for people who have worked with Idris or Agda or whatever. We have type holes. We have type direct development, which is advertised by Idris. Like if you write this symbol here, and it will say there's a goal of type. This is an expected type, and it will normalize the expected type here, in case it's not clear. We also display the context, and in case we have hidden a variable, like shadowed variable, we will say the shadowed variable is not in scope. This is in case when you have 2 variables of the same name but different type. It tells you which one of which type is available in the current context. And here's a hello world example that everyone should already seen in tutorials or something, in the theorem proving of a dependent type language, which is very simple. We define an infix plus function for the natural number. The natural number is defined like several slides ago. We do pattern matching on the first variable and return the obvious thing. We find it tighter than equal sign. So in these expressions, plus will become an expression before equal sign becomes an expression. I hope you understand my wording. There's the right identity rule for plus, which is obvious. We do an induction on n, and there's a left identity rule, which is by computation. So it is nice that we can prove some of these by computation, but not everyone. Like we have to prove that the right identity rule propositionally, also the this rule propositionally, and then we do some obvious rewriting in the end to prove the commutativity of addition, which seems nice, but can we make it simpler? So here's a question. what if we can put the right identity rule and this strange lemma right into the definition of add? Like we have 4 clauses for the addition operator, and we just reduce all of them if they match. Someone says no. This is what Cox says. Cox says no because Cox uses eliminators or case trees. They only allow single variable pattern matching. So it doesn't make sense if you pattern match 2 parameters at the same time. Cox even tells you to remove the last clause. So it's very disrespectful to our work. So IR supports this. If you add the overlap keyword before, like after the def keyword, IR will regard this function as an overlapping and order independent pattern matching function. So
Just a sec. We have a question in chat about
okay, let's
how
look.
how variables that are shadowed appear when you display a goal or a type when you inspect a whole.
When inspecting how do the shadow variable is? They just appear in the same way. We haven't write any special pretty printing things there. We expect to pretty print them to HTML so users can like click to go to definitions. Yes. So here's the thing. Here's the thing. We have this. So if you write some definitions, we can there's a way that you can browse the code with usages highlighting, and hopefully these can solve your find definition problem, like solving the alpha conversion problem. You can tell the difference of different variables of the same name. You can see from here. I don't know if this will help anyway. Yes. Okay, so I hope this answers your question. Let's continue. So we have this definition where the right identity rule is part of the definition and also the lemma is a part of the definition. By that, we can prove the commutativity of addition by one induction, which is nice. Like when we pattern match on A, A becomes 0 on both sides, and the 2 of them reduce to B, which is the IDP means identity path. It is another way of saying reflexivity, but it's something in homotopy type theory. But it's the same idea. When we pattern match on A with suck A, then A is replaced by suck A in both cases, and in both cases it's replaced with suck A plus B. You have to be confluent, and so basically when your pattern matchings are overlapping and order independent, you want the patterns to be confluent. So consider this case. If I replace the second clause, the body, with 0, so it becomes no longer confluent with the third clause, and IR knows this, and it tells you that your function definition is malformed. It says that the second and the third clause is not confluent because the second clause is 0. Like they match the same input. When you put suck A and 0 to this function, the second and the third clauses will both match. But the first clause will return 0. The second clause will return A plus something. There should be a normalized expression displayed, but it should be available in the terminal. Maybe it's the problem of the IDE. So, but it knows the difference. It normalizes during the conversion check. It's just that this is a problem of the pretty printer. But it doesn't matter for a showcase, right? We also have so this is one of the many features we have, which is very nice. we simplify a lot of proofs. And there's another feature, which is another new feature, which is the reduction rules in constructors. This idea comes from a rejected paper. We're planning to resubmit it elsewhere. So if you are ESOP committee or reviewer, please stop watching. Okay, so here's the feature. We have reduction rules. We have partial reduction rules in constructors. And how is that useful? When we define integers, we can use two constructors to represent integers, and like we can add a positive sign before a natural number and a negative sign before a natural number to represent integers, which seems nice, but by that we have two zeros, a positive zero and a negative zero, which is not nice. So what if we do this? We just equalize negative zero with positive zeros. So like negative zero reduced to positive zero, so they obviously become the same term. And yeah, we can do that. And inspired from this feature, we need so by the duality of inductive types and records, um, we also introduce reduction rules in record fields. So these two types are dual to each other. So like a function from int is an elimination of int is kind of equivalent to an introduction of int elim data. And um, uh, and so basically, if you don't understand what's going on, you just need to know that we have added reduction rules to inductive types constructors, and due to some weird reason, we also think that it's necessary to add reduction rules in record fields. Um, so how is this thing useful? Like we make integers more beautiful. Like we no longer need like next suck kind of things in Agda, or I don't know how the people do in Idris. We also don't need to make a third constructor like in Cog, which we believe that it's nice. And this might be useful somewhere else. If you have the so here goes. So I'll say something about cubical type theory. If you don't know cubical type theory, you can ignore it. So in cubical type theory, we have higher constructors in higher inductive types. And in these constructors, we're having some constructors with special reduction rules when applied by interval variables, and we can do precisely that with partial pattern matching on intervals, and we support that. And so you can define higher inductive types with IA in that syntax. And we can also define the path type as a record with conditions. So this feature is called conditions, and you can define the path type as a struct with reduction rules. The path type is a struct with a function from interval that the left hand that for input left and the right interval we have known the output value. So that's the thing. And so here comes a new idea. So look at this int lm data. It's a struct with two fields, and one of the fields reduces when applied by certain variables. So what if we can do this? So this is a pseudocode that doesn't work obviously because I think it's not confluent. Is it possible to do this? Like, we have a record with two fields. It's a monoid with a carrier A, and we have an identity element unit. We have multiplication operator, and when applied by unit on the left hand side, we reduce to the other operand, and we have the other rule for when unit is on the right hand side. This looks nice because if we can do this, like we can make the left identity rule and right identity rules by definition. This is true for most monoids, most instances of monoids. It might not work for like free groups or something, but it should work for like natural numbers and integers and lists and many others. Many other types. So if we can do this, we can. So basically, in type theory, it is good that we can simplify some proofs by computation. But when you reason about structures or mathematical structures abstractly, we lose those definitional equalities, which we have to rewrite those properties by hand by applying the elimination rules of identity types, which is not nice. Because if the compiler knows this equivalence, then it simplifies it by itself. Some people from the new Perl community says it's good, and it's unacceptable to give up equality reflection. But we want disciple type checking. So this is why we're here today. But what if we can recover some of these extensional equalities? Like we can quantify over extensional equalities in a decidable way. And is it possible? Yes. If we can do this, then it's possible. But we need to figure out the details. So here's what I've got. What are we expecting from this? We're expecting unit, which is a field, to be instantiated as a valid pattern, which we can so that we can put it on the left-hand side. So if it's a function application, you cannot put it here because function applications are not patterns. So we have to allow to ask them to be instantiated as a pattern, so they can be put into a position where patterns do. And this idea coincides with pattern synonyms. So we're like making pattern synonyms a first-class citizen in the language. So we can quantify over pattern synonyms, and then we can put these quantified pattern synonyms in the pattern matching. And of course, we don't know the pattern synonyms to be covering or not, so no way to put them here. Like no way to put them in the function definition, but to quantify a pattern synonym in the function definition. But anyways, we want these. We want when you apply the multiplication operator of a structure called M and pass in the unit element of M, we want this expression to reduce to Y. So when we work with monoids abstractly, the abstract unit applied to abstract multiplication should reduce according to these rules. And if we have that, we can recover what I said just now. And this feature is yet unimplemented. It's planned in the near future because I think this is an interesting feature to work with. Andres Kovac says this is interesting. So I guess this might be indeed interesting. I don't know. If you go to the WITS workshop of Popo next year, January, you might meet me in real life, and you might listen to me talk about these in a more serious way. So there are some shameless self-promotion. Aya is looking for open source contributors. We have something that we need help. It's written in Java 17, so we have so even though it's Java, we have pattern matching, we have Silk classes and records. Yay! And also, I'm an undergrad looking for a doctoral position in the US. I'm applying next year, so there's my profile. You can find these slides in a lot of places in Discord. So I guess I don't need to send this again. So it's in the slides. And DM me if you are interested in hiring me. So that's the end. Any questions? And anything I didn't make clear? Here are some footnotes that. So I made two jokes about two inner jokes. The teddy bears is from chat. Also, that Idris is using complex number for specifying precedence is also a joke. It's actually a natural number. Okay, here are some questions. What is the core difference between Aya and Aaron? Oh, okay. So Aya supports overlapping pattern matching, and Aaron does not. And Aya supports records with reduction rules. Aaron only supports inductive types with reduction rules. And also, Aaron is written in Java 11, and Aya is written in Java 17. And Aaron has IntelliJ IDEA plugin, but Aya has a VS Code plugin. Do we need to prove that? No, they have to be definitionally equal. And confluent means reduction have to see in there. No, there are actually some complicated Yeah. But I'm sending the messages here, so for the record. So your model example is interesting, thank you. And when it checks overlapping clauses, doesn't try to unify the overlapping clauses before. Mm, it does. It's just it pretty prints them in the way that before unification. If there's no unification, then most of the definitions you'll see won't type check. So um, you plus probably need to interleave termination checking and confluence checking. Yes, probably. Yeah, we don't have termination check right now. We are waiting for a friend to do that. So I'm making this talk so in case Idris people have some ideas that I can steal from you guys, and maybe you can also steal some ideas from me. If unit now needs to be a pattern synonym, then I guess you can write an instance corresponding to the monad for. Yes, we can. In that case, we have to use the traditional one. Yes, I guess make judgments equality non-transitive. ID. Oh yeah, there should be some problems about that. But these functions are abstract, so basically some abstract things are reduced. So they're not supposed to reduce before. Yeah, then they're not transitive. Like if you rewrite with transitivity, then something just magically reduces. That's all what I want to achieve. If you remove this, then it should be transitive. Unifies the overlapping clauses. Yeah. I mean, currently, so basically, this is pseudocode. This is pseudocode. Aya thinks that this unit is a catch-all pattern, so it says there's an error. It's not like it's not even resolved. Well, it doesn't work. Oh, it doesn't work because we haven't implemented it. So basically, this page describes what are we gonna do. But we didn't implement this, but we have this. This example works. So because we need this syntax to define the path type, to define the equality type. And there are some complicated showcases, like red black trees written in Aya, which we're very proud of. But we haven't reached the level of usability as Idris does, because Idris has been developed by great people for great many years. Aya is only developed for a year. Do you have any more questions? Like maybe something's confusing? I just don't know what you don't know. If you're willing to let me know, then please. Oh, thanks. So there are some novel features which I believe should work. This should not be very difficult. We just need to check, have a pattern synonyms check, and allow some abstract reductions. And this overlapping pattern matching should be more interesting. It also breaks transitivity of definitional equality, I believe. But it's like it's obvious. Like we just put the pattern matchings as reduction rules, like automatic reduction. It's like adding some automation in the language in a very simple way. in overlapping pattern different. Oh, the implementation is different. Check out about rewrite rules. Yes. So Jasper's paper did not do a good job on the implementation. He tried to unify each two clauses, and if two of them are are actually overlapping, then we we unify the bodies. We build a most general unifier from the patterns, and we build we try to unify the bodies after applying the unifier. And in Aya, we did something different. We built a case tree. We built a case tree where there might be multiple expressions in the leaves. So take this example. The case tree has four leaves. We have 0, 0, 0 suck, suck 0, and suck suck. In these four leaves, like the first leaf, we have two expressions in the body. We have 0, 0, and 0, 0. And in the second one, we have 0 suck, the first clause, and 0 suck, the last clause. And we just classify the pattern matchings by the same algorithm in generating case trees. And by that process, we check coverage. And after checking coverage, we already know that which clause it might overlap. So we check for fewer numbers of unifications. So this should be a more optimal algorithm than Jasper's implementation. What's the spec for universe level? Oh, we have universe rigid variables. We have universe to be soft, which should be called flex variables. We have a successor operator. We have a max operator. That's all. And preferably, we should be able to define when our function is parameterized by two levels, we want to be able to specify like one of them is lesser than the other. But we haven't implemented that. Aaron supports that, but I'm having a hard time reading Aaron's implementation. The code is really messy. It's written in some industrial Java style, which yeah, I used to be working in Aaron and I was having trouble understanding some of their code. Yeah, I hope so. It's first. Okay, thanks for telling me this. Thanks for telling me this. Maybe it will help me with that. +1. There is this one is based on case tree too. I don't know. I asked Jasper. He said it's kind of. Well, I can rewrite that if it's simple enough. I don't know. I don't know. Can't make any bets right now. Any other simpler questions? Because maybe I should stop recording or something. Because this is extensive discussions, which I'm willing to join, but maybe recorded video should have more relevant questions. Okay, welcome. I hope you find this interesting as people in AIM find Edwin's talk interesting. This one use case trees too, really? I hope I'm wrong. It's just for lying to me. Hmm. Oh wow. This is a case tree, but I don't think it contains multiple function bodies. So it's not. And our version is kind of different. Here's a draft that you might find interesting. Not find explanative. Like this is a max function, which is a simpler case of overlapping pattern matching, and we classify them in this way. We have 4 classes, and the first class have 2 function bodies. First, note that there are 2 function bodies, and unlike the case tree Jasper builds, we build a multi-case tree where there are 2 leaves, 2 expressions in the leaf, and so we have less definitions to be unified. Anything else? Is it a good idea to stop recording now? Let me just check the other. Okay, there's no new information. Yes, we use the same mechanism to check for both confluence and the coverage. Um, that's why I believe it's optimal. So it's a novel work which has some benefits. Okay, I'm gonna stop recording. No more questions seems. You're welcome.